Okay, thank you so much, Roland. And this is actually something that came out of the discussion that we had on Monday after the school. So some of you asked if you could actually have a bit of an overview or like a tutorial on how we could perform the space-time decomposition of Einstein's equations using xTensor. So here on the program website, as Roland said, I have the notebook that I'm going to run now. So if you want to follow the example locally on your laptop, you can just download it. You also need to install the xAct package that you can find here on the website, or if I go to the next tab on the download, you would download here this zip or tarball and then install that. So we're not going to take the time to do this now because I announced it a couple of times over the last few days. So I would just go over the notebook that I have here. If you do have any questions, just interrupt me or type it in the chat and Roland will interrupt me because I may not be able to see your question immediately. Okay, so this is the notebook that we have, just to put everyone on the same page, some general information and notation convention. So again, in this notebook, you will find the link to the website. This library is free, so this package is free, even though Mathematica itself is not, and was developed originally by Jose Maria Martin Garcia, who used to work in numerical relativity and gravity. As you will see as we go through the notebook, if you're not familiar with xTensor, that we can actually use it to perform abstract index tensor calculations. And the notation in xTensor, if you have tensor with lower indices, you would note them by minus and then your index label, etc., etc. Tensors with upper indices would just be labeled as name of the tensor and then that index label. Here I am using G to denote the space-time metric with a signature minus plus plus plus. N will be the unit normal vector. So this is really using the notation that I introduced in my lecture on Monday in the beginning. Gamma will be the induced metric. I use geometric units. And one slight change to maybe the more common way of writing down Einstein's equations. I will write all of my equations as equation equals to 0. Which means that if I manipulate my equations, I know that I'm always manipulating something that in the end gives me 0. So I make much fewer mistakes than having first the right-hand side and then the left-hand side. So I will write down Einstein's equations later on as Einstein tensor minus 8 pi energy momentum tensor, or in its trace reversed form, where we have the Ricci tensor and then this combination of energy momentum tensor and its trace. Okay, so that's just notation. So let's start loading xTensor. So to do this, you would just use here xAct and then xTensor. We will also use expression manipulation, which is included in the table that you will have downloaded from the website. Okay, good. So one more just notation thing that I will use just to make the output look nice. I will say, okay, any preprints or any of the indices. So I say here screen dollar indices, which essentially in the end of the day will give me a number for my indices. I will also use the minus sign for the extrinsic curvature. Remember when I introduced the extrinsic curvature, KAB equals -1/2 Lie derivative along the normal vector of our spatial metric, of our induced metric. If you look, for example, in Wald, you may find a plus here. Yes?
Will you also answer questions concerning how to get the thing to work on a Mac, or only questions that have to do with science?
I can...
Somebody has a question where they get an error message when they try to run xTensor, where it says xperm.mac can't be opened because Apple cannot check it for malicious software. I don't use a Mac, but I remember I could change that by going to the security settings.
Okay, so I am running it from a Mac right now. I haven't encountered this particular error. Make sure you have you store the library in the right directory. So for me, it essentially worked out of the box. So if I look at my, and that's why I actually kept this open here. So I don't know whether you can see this, but on my Mac, I have the tarball in applications mathematica.app contents add-ons applications. And for me, it was just moving it there, and then it worked out of the box.
It seems it's being resolved in the chat. It seems a known issue, and the URL was pasted in there. I think you can continue. Just will be sorted out.
Okay, very good. Yeah. Do we have any other questions at this stage? No. Okay, so as I was saying, so this is just a definition here. I will define the extrinsic curvature with a minus sign so that our normal vector and our time slices will be future directed, and likewise for the acceleration. So I just run this here. Then the next point is just defining our manifolds and our matrices. And the first thing that I do here is defining just a list of indices that I will use for my indices. And then I start defining a manifold. You can do that with the command def manifold. The name of the manifold here, I just call it M. I have a manifold in 4 dimensions. So I specify this here. And then I provide this list of indices as index. In general, because I think Thomas is probably also still here. So if you're interested in, for example, high-dimensional spacetimes, you could also change this number to either D or a specific dimension. And then we define a metric with a def metric. The first entry is signature, which is for us minus plus plus plus. Then I name it GG. So whenever I input it, I would input it as GG for the metric. But print as just single G for the printout, and then the covariant derivative with respect to the spacetime metric, I label as capital C, capital D.
Question? Can we handle a manifold with 2 time index?
With?
Oh, sorry. With 2. I mean, for the metric, the diagonal part, maybe 2 minus 1. Is that possible to handle with xAct?
So if you want opposite, so the opposite signature, you would change this very first entry here.
So it will be plus 1.
So if you were to use the notation plus minus minus, I think this should be.
The question is if you have 2 time variables, time, dream time.
That I don't know. I'm sorry, no, that I do not know. I would say look at the documentation.
Okay.
Yeah.
There will be a question.
Okay. Good. Okay, so yeah, and if we define our manifold and define our metric, then xTensor automatically already defines our Levy-Civita symbol and tensor. We have our covariant derivative, we get the Christoffels, Riemann tensor, Ricci tensor, etc., etc. Yeah, so you can find all the definitions here. Okay, good. So that's our metric. Then we also, just in preparation to what's coming next, I am here defining just a bunch of tensors. So you don't have to go through this in very much detail, but just to give you an example. So if you want to define a scalar or a scalar density, you would define the tensor with a respective name, and then just empty brackets, which indicates it's a scalar on our manifold M. So in this particular case, I here define the Lagrangian and the action. If we want to define any of the 2 tensors, you would do that in the following way. So again, def tensor, then the name in my notation TMN is for energy momentum tensor. Then I have 2 indices here, A and B, on my manifold M. And in this particular case, I want these tensors to be symmetric in A and B, and I can define this in this fashion. And the other definitions here are essentially the equations of motion for the tensor and the trace reversed version thereof. I can also define constant symbols in this fashion. So if you were to, or if you would be interested in adding, for example, a cosmological constant, or you want to keep your coupling constant general, you could define it in this way. And here I'm just defining them and then define a rule that I will apply later on what this gravitational coupling constant would be. And I will focus on asymptotically flat spacetimes. So I will put cosmological constant to 0. Okay, so let me just execute that as well. Good. Then next, we want to define our 3-dimensional or our 3+1 quantities. So we have here our time-like normal vector. Again, we def tensor, then the name now with 1 index A on our manifold. And then I define a rule that will be applied automatically whenever we have this combination, which is essentially the norm of the normal vector, which will be replaced with -1. Yeah, because that's the normalization of the normal vector. So I just let it recognize that automatically. And then we define our 3 metric. As I said, it's labeled as gamma. So here the signature is +++. That's how I indicate this here. Name it as gamma AB. The covariant derivative is now called little cd with these symbols. And I also tell in the definition that this metric is actually an induced metric from the form metric G and the normal vector N. And this is how we project it. And then I just have a rule here where I say, instead of using just a symbol for the projector, actually replace this symbol with the 3 metric when I do the computation. Good. So we have all of this here. And then the last bit, I'm defining the lapse function and introduce a rule where I replace the acceleration with respect to the normal vector with this particular combination that you can show just in a few lines on with pen and paper, and that I usually find quite useful. Okay, good. Yeah, let me just take one example. No, I don't think we need that. We can just go through in the following. Maybe one more thing that we will use further below. If we want to write down our equations of evolution equations, not in terms of Lie derivatives along the normal, but actually as partial time derivatives, we can introduce a parameter, so def parameter t, which will be our time label. I'm also introducing a tensor that is a shift vector here on our manifold M. Remember, we said on Monday that the shift vector by construction is orthogonal to the normal vector. So I can actually include that in the definition and say this tensor here is orthogonal to n, which means that whenever we have combinations, contractions thereof, they will be put to 0 automatically. And I also say that this tensor is projected with our induced metric or projection operator. Okay, and then
interrupt again. So here I saw that the 3 metric is with a down index and up index. What if I change it to all down? What will happen?
So in this case, I've used this combination because I have my shift vector defined with an upper index. So the projection here.
So I mean, this format is really required, or maybe it just need to know the magic tensor.
No, so here you would essentially want to contract over one of the indices, right? So
okay.
That's why I put it in this form. Okay, yeah, and then just one last rule that we will use in the end is that I say, okay, whenever I see the Lie derivative along the normal vector on a tensor, then I want to replace it essentially with this definition, 1 overlaps, and then we have here the Lie derivative along t, which is really just a partial derivative, and then the Lie derivative along the shift vector. Okay, good. So now we've set up everything that we need. We just collapse this part here. Do we have any questions just on the definitions? Okay, so if we don't, then let's continue with the actions and how we can actually derive the equations of motion from the action, because I thought that may be a useful application for you as well. I'm not going to go through, so I've defined some substitution and simplification rules. I'm not going to show all of those. Let me just execute this box or evaluate those boxes. Then we next define our Lagrangian for the Einstein-Hilbert action in 4 dimensions with a cosmological constant. So here we have our Ricci scalar. The CD here indicates that this is a Ricci scalar constructed from the form metric. And then we have defined before our cosmological constant. Then we can define the action. Just a note of caution. So in xTensor notation, let me just phrase it the other way. So we know that the action in principle would be an integral over a square root of minus the determinant of the metric times the Lagrangian. In xTensor, the action is defined without writing the integral. So you have to remember that this equation actually implicitly will have an integral here. Yeah, so now it's just adding the volume form in front of our Lagrangian. Okay, good. So now we have our action, and to get our field equations, we know that we need to vary this action with respect to our metric. Before we do that, we have to do some work at least, because we if we were to just take the action that we had before with the Ricci scalar and perform the variation, then we wouldn't actually get anything out of it. So if I just do this, and were to use the variation of this with respect to the metric, then it would only vary the part where we have the metric explicitly, which was a square root of the determinant, but it wouldn't vary the Ricci scalar. So in order for it to do this variation, we actually have to say, okay, replace the Riemann or the Ricci scalar with its notation in Christoffel symbols. And this actually is already enough to then have the variation of the Christoffels with respect to the metric. So this is kind of this intermediate step here. And now what we are doing next is indeed varying. So you have this command var_d. Then you say which quantity you want, with respect to which quantity do you want to vary. So in our case, that's the form metric. And then this is the action that we want to vary. And I've already multiplied the entire expression with the 1 over square root of minus the determinant of the metric, just to make it more readable. So this is what you get if you vary our Einstein-Hilbert action with respect to the metric. Now, of course, this is not really in the form that we know and love. So now so I have defined some rules locally that allow me to collect these appearances of the Christoffel symbols back into the Ricci tensor and Ricci scalar. And this is precisely what we have here. And now we have our Einstein field equations in 4 dimensions with a cosmological constant. Okay, and as I said before, we also want to okay, no, wait. So sorry, this is an intermediate step that I think we don't actually need. So if you want to keep your energy momentum tensor general, then you can add it in by hand afterwards. If you know already explicitly what your meta content is, you can also add that to the action and vary with respect to those meta fields. So there, but I'm not going to show this here.
Question in the chat before you get too far ahead. There's a question: does var_d automatically discard total derivatives?
Say again. Does automatically?
var d automatically discard total derivatives?
I don't think so. So I'm not sure. So the honest answer, I don't know, but I would not rely on it. Yeah. So something that you can check at home, I would say. Okay, yeah, as I was saying, so what you can do is, if we will have the general energy momentum tensor, we just add it here. And then what we will also need later on is a trace reversed form of the field equations, which will be used when we derive the evolution equation for the extrinsic curvature. So this is what I'm just doing here. Okay, good. So this is how we would get the field equations by varying the action using xTensor. Do we have any further questions here at this stage? Good. Is there anything else in the chat, Roland?
Not at this point.
Okay, very good. So then let's collapse this part. Oops. I will not go over the next section, so you can do that at home, where we just derive the projections of the energy momentum tensor. So instead, let's just focus on the vacuum field equations. And again, the first, let me see, do I need to show you what we do here? No, so I've already talked about all the definitions. So the first two you can just execute. Here we are defining a couple of tensors, for example, our Hamiltonian constraint, our momentum constraint, and the evolution equations. And I also define some simplification rules that you can look at in detail later on if you like. So at the moment we can just evaluate those two cells. Okay, so the next one, well, the geometric relation, this is kind of overkill, but was just to have everything consistently. So remember, the geometric relation or kinematic equation came from the definition of the extrinsic curvature in terms of the metric. And that gave us the relation between the time derivative of the three metric and the extrinsic curvature. So here we're essentially just writing a Lie derivative of our metric along the normal vector minus, and writing out the normal vector equals to 0, such that we can explicitly write down dt gamma. So just this is really just for completeness. Yeah, so this is something that we've already seen on Monday. Time derivative of the three metric equals -2 alpha times extrinsic curvature. Okay, so that was the easy part. Now let's go to the field equation, Einstein's equations in vacuum, and let's actually look at first the decomposition and then the different projections of the field equation. So what we are doing now is that we write out the Einstein's equations in all the components that would either so you can reconstruct any four-dimensional tensor by writing it as a term that is fully contracted with the normal vector. So this would be the first term here. We have one term that would be fully projected onto the hypersurface, and this will be the term here in the end. And then we will have a term where you contract one of the indices with the normal vector and the other one is projected with the three metric. So this is here. And I'm usually using this decomposition in general because then when I contract with n or project with gamma ij, sorry, with a projector, some of these terms are automatically recognized as being 0. So this is a very, very first step here that I say, okay, I take my four-dimensional field equations that I derived before, and I induce this decomposition with respect to our induced metric or our three metric. and the normal vector here. I am also applying, okay, so maybe I can just show you in a bit more detail what's happening here. So if I were to just perform this induced decomposition, here what I would get is the following output that I say, okay, I have my, for example, Ricci tensor here fully projected with a 3-metric. Here is what I said is this kind of one of the indices is contracted with a normal, the other one is projected, and so on and so forth. Now, I personally don't like this output very much. That's why I've defined a rule where I replace this projector directly with a 3-metric. Yeah, so this writes out explicitly the projector in terms of gamma ij. Now, there are a couple more things that you see here. So first of all, there's also these red brackets where, which is essentially a contraction, and A and B here are dummy indices, but we also use A and B as our free indices. So I'm not very fond of this kind of double notation. So if I include the no scalar command, then it will replace all of these dummy indices with actual different symbols. So I find that a bit more convenient. And then the last thing, if you look at this output very closely, you see that we still have expressions that involve the 4-metric. So I want to replace the 4-metric fully in 3+1 quantity, so with a 3-metric and the normal vector. And you can do that very simply by just using metric to projector. And that will replace all the occurrences of the 4-metric with its relation to the 3-metric and normal vector. Okay, good. Last thing that I've been doing here is to put the energy momentum tensor to 0 so that we are focusing really on the vacuum case. Okay, very good. So that was the first step, and that so usually I wouldn't write this out separately. This is more to show you how we get here. And then the next step is to replace the Ricci tensor and Ricci scalar, the 4-dimensional Ricci tensor and Ricci scalar that we still see here, with their relation to the 3-dimensional Ricci tensor and Ricci scalars and the extrinsic curvature. And remember on Monday I said there are these relations. I didn't actually write them out because they are a little bit lengthy, and they're known as Gauss-Codazzi equations. Nice thing is xTensor already knows about the Gauss-Codazzi relations. So what we can do here is actually take the expression that we just derived and apply this command Gauss-Codazzi onto this equation. And again, I can maybe just do this explicitly so that you can see what's coming out of here. Yeah, so what you get here now, and this is still very lengthy, is essentially every time you see a Ricci tensor, 4-dimensional Ricci tensor or 4-dimensional Ricci scalar, it's going to be replaced by its relation to the extrinsic curvature. This R with a capital D is now the 3-dimensional Ricci scalar, and there are relations to derivatives of the extrinsic curvature. Okay, and also.
Sorry, there's just a Mathematica question, I think. It says by Thomas Andrade, I'm a bit confused about the rule replacement, / and the function evaluation //. Could you comment on that?
Okay, wait a second.
You may have to read that.
Yeah, I think I will. Okay, let me see. Okay, so so slash dot. So wait a second, Thomas. If I take okay, I want to close the chat again. Okay, so maybe just here, since we are here as an example, so this would really be a replacement, right? Whereas this // this is a command. So here this two canonical, for example, does a simplification, or we also have, so I haven't gone very in much detail through the command. So this is a rule that I've defined. likewise here, right, where I just say, okay, if you see this occurring, replace it with this. So in this case, I just want to set the energy momentum tensor to 0, whereas the double slash are commands that are already defined within xTensor. So here this double slash metric to projector is a command already defined in xTensor, or to canonical is kind of, so it's not necessarily a simplification, but it does bring all your terms into a canonical form where, for example, your indices would be ordered in a certain way such that you, they would be ordered so that you can actually identify terms that are the same by symmetry, right? Does that answer your question, Thomas? Okay, good. Okay, yeah, so as I said, so if you act with the Gauss-Codazzi command on our expression, we get this rather lengthy expression here, but we can simplify that further. So now I again have a combination of applying rules that I've defined myself, like this one, where I replace the occurrence of the projection operator with the 3 metric. Then this no scalar and metric to projector is already defined in xTensor. Next one, grad normal to extrinsic k, is also super useful, where any occurrence of the gradient of the normal vector will be replaced by its relation to the extrinsic curvature. So again, if I can just put an example in the line above. So imagine you have something like this, where you take the covariant derivative of the normal vector. If you now apply this grad normal to extrinsic curvature, you would get this relation minus extrinsic curvature minus this combination of normal vector, and that's actually the acceleration that I'm just automatically replacing. Okay, and then simplification is a very nice way of simplifying your equations, which is a bit more powerful, and so it's defined in xTensor. It's more powerful than the standard Mathematica simplify, because it already knows about the tensor relations. Okay, then again, some rules that I defined myself for further simplification, and then we end up with this general expression here. And now what you see, we have terms that are already fully spatial and only contain quantities that live on our hypersurface. And we have other terms that still contain the normal vector. And that will be useful for us when we do the different projections. Okay, let me just execute this command here. And then we have the same for our trace reversed field equations. So I'm not going to go into the details of the commands here, and just execute this as well. Good. So, and what we are going to do now next, at least conceptually, is to take our field equations decomposed in this way, and we will perform 3 types of contractions. So the first contraction will be of both indices contracted with a normal vector. This will actually give us a Hamiltonian constraint. Let me just go here. So this is the first one. This will be our field equations contracted both indices with a normal vector. The next step is what I call a mixed projection. So here we are contracting one of the indices with a normal vector and project the other one with a projection operator. That will give us a momentum constraint that we've seen on Monday. And then finally, we will project out both indices onto the hypersurface, and that will give us a evolution equation for the extrinsic curvature. And Roland, how am I doing on time? I'm not actually seeing the timer right now.
So you've got 11 minutes time.
Okay, very good. So I think that should be enough to give you at least an idea what we're doing here. So yeah, as I just said, the Hamiltonian constraint is contracting the field equations in both indices with a normal vector. So that's what we're doing here. We take the equations that we just decomposed and then contract with n. And if you do that and simplify this a little bit, you get precisely the equations that we have here. There's one term that so this is all nice. So we have here our extrinsic curvature, our three-dimensional Ricci scalar, but we have one term that's not very nice. It still contains a normal vector, which is this one here. But what we can do now is that we say, okay, I want to replace this combination that also still has a four-dimensional covariant derivative with my three-dimensional derivative. And what I can do is apply this command to induced derivative, acting on my quantity on my variable, and then going from CD, capital CD was our four-dimensional covariant derivative, to little cd is our three-dimensional covariant derivative. I do some simplification, gives us this relation. Here again, we see this covariant derivative of the normal vector, but we already know that this should give us terms involving the extrinsic curvature. So we can, in the final step here, just again say replace the appearance of a gradient of the normal with extrinsic curvature, do some more simplifications, and we get the Hamiltonian constraint as we've seen them on Monday, plus a term that comes from the cosmological constant. And since I've defined my field equations equals to 0, we already know that this h that we have derived here equals to 0. So this is what we get. Okay, so that's our Hamiltonian constraint. Any questions at this stage? Good.
There's one in the chat, 1 second.
Mm-hmm.
No, that was for me. Never mind.
Okay, good. Oops. Okay, so next one, this mixed projection. Again, as I said before, so we take the equations of motion, project one index with a normal, the other one with a projection operator. We do that, we simplify that, and then we automatically already get our momentum constraint in vacuum, where we have the divergence of our extrinsic curvature minus the derivative of its trace. Maybe one note of caution here that I haven't commented on just yet. So here you see, and we did that for the Hamiltonian as well, in fact. So you see that we have contracted some of the, or both of here, both of our indices. So that is to say, what we take here as index B and index C are really dummy indices. And for xTensor to know that these are dummy indices and not fixed, we actually have to give, have to say this is a module and list those indices that are dummy indices, so B and C here in this case. And I'm saying this because if you don't use this module, then xTensor internally will always, so will hardwire B and C in here, so it won't recognize this to be a dummy index. And this can be complicated if later on you do some further manipulations and you have expressions that in principle are the same because they should be dummy indices. It may not recognize it unless you have defined this as a module. So yeah, so try to keep this in mind. So whenever you have something where you basically have a dummy index, apply this module so that xTensor knows later on this actually was a dummy index and can replace it by something else if necessary. Okay, good. So this was our mixed projection. Now the final one gives us the evolution equation for the extrinsic curvature. Turns out that it's actually more useful to use the trace reversed form of our field equations. That's why we have defined it earlier. And we are projecting our trace reversed field equations onto the hypersurface in both indices. So here, let me just go from the inside to the outside in this expression. So we have our decomposed field equation, trace reversed form. We are projecting in both indices as gamma and do some simplification. And at this stage, I'm already applying some simplification rules that I've defined before that you don't have to worry about right now, but you can go step by step later on if you like. Now,
in the chat.
Okay.
why did we not have to use a module for previous dummy indices like those we used / no scalar with?
So again, so this no scalar is already, so it's already defined in xTensor, so it should already do precisely that internally.
5 minutes.
Yeah, so okay, so Thomas, this no scalar is already defined in the xTensor or xAct package, so I didn't have to do that myself. Does it answer your question? Good. So yeah, where were they? Okay, yeah, so once we execute that, we will, so if you were to go step by step, you would still find terms that go like the 4-dimensional covariant derivative acting on stuff, and particularly acting on your extrinsic curvature. So to rewrite all our derivatives in terms of either a Lie derivative along the normal or as 3-dimensional covariant derivative, we again apply this command to induced derivative, going from the 4-dimensional derivative to the 3-dimensional one. I'm again applying this predefined command gradient of the normal vector going to the extrinsic curvature, do some simplifications. And there's also this command contract metric that will explicitly contract dummy indices where applicable, and then just ordering everything in a canonical form. And if we do that, we find this equation. So here we already have a Lie derivative along the normal of the extrinsic curvature, which contains a time derivative, precisely what we want. And then here you have your derivatives of the lapse, 3-dimensional Ricci tensor in terms of the extrinsic curvature. Now, the last step that I'm doing here is just for convenience, because I would like to write out the time derivative of the extrinsic curvature explicitly. So what I'm saying here is, okay, take this equation, curly p that I derived here. The way I defined it, I know that p equals to 0. That's great. So I'm taking this expression now, say replace the normal vector with the time derivative and the shift vector that I defined in the very beginning equals to 0. And then take this expression and solve it for the time derivative of the extrinsic curvature. So this defines a replacement rule here. And then I'm defining this quantity dtKij, right? Basically use this rule that I just derived to write down explicitly what the time derivative of the extrinsic curvature is. Okay, so here we are basically done with the derivation. I know I only have 3 minutes, but let me stop for quick questions. And then there's one last thing that I want to show you, which I find particularly useful, where we can where we can output all of these equations in terms of LaTeX files.
2 minutes.
Okay, so any more questions?
Sorry, so I was muted. There's a question in the chat by Fran Silva. Can I do this decomposition for a different Lagrangian, like the one for f of r gravity, for example?
Yep. You most certainly can. So you would have to basically adapt this notebook or write your own to do this. So for all the modified gravity simulations that I'm doing to derive the equations in 3+1 formulation, I do the equivalent type of calculation as well. So yes, you can certainly extend this to other Lagrangians. I just thought connecting to the lecture on Monday and to give you a neat example, let's focus on Einstein's equations in 4D in vacuum. Okay, good. So final thing that I would like to show you, because I think it's super useful, especially if you go beyond Einstein
1 minute.
Gravity, is to actually have a way to output all of these equations in LaTeX format, if you want to then type it up in your notes or whatever. So xAct also has this package xAct. So it's part of the xAct bundle that you have downloaded before. And then you can use these type of commands. So what you have here is you export. This is well, the path
30 seconds.
and the name of the TeX file that you want to create. You say TeX print of the quantities, in this case, the Hamiltonian constraint, and then as text. And the others are likewise for the momentum constraint and the time evolution equations. That's part of the reason why I defined dt of the 3 metric before, so we can just execute those. And if you give me a minute, because I think I stupidly
5 minutes.
Okay, I'll stop in a second. I just wanted to show you the output that you get, and then I'm stopping.
It's automatic. Show away. It's all automatic.
I know, but I shouldn't do this really. So, PR split. Okay. So if we just look at the Hamiltonian constraint TeX file, I hope you can see this. So the output would look like this. So we have -2 lambda, extrinsic curvature combinations, and the Ricci scalar. So you may have to do some manipulating afterwards, but in principle, you can output this as TeX file. And I will stop here because I know we have to continue. Any quick questions I can take now. Otherwise, we can talk after the lightning talks. Thank you.
No questions in the chat.